In the previous video, we were able to determine differential equations that govern the behavior of the charging RC circuit and discharging RC circuit. These equations are going to be our starting point in this video. There won't really be any visuals in this video, just going to be straight integral calculus, so buckle up. Let's start with the charging scenario. How do we turn this, the differential equation which we got from applying the loop rule to the circuit, into these, the charge and the current as a function of time? We found it useful to solve for dq by dt, which is not only the rate of change of charge on the capacitor, it also happens to be the current in the circuit, since I and dq dt are both positive. So I'm going to present that rearranged version of the equation that we ended up with from the previous video. We're going to use this technique called separation of variables. You might have heard of it before, but the way it works is we want to get all the q stuff on one side and all the t stuff on the other side. Here we only have dt in terms of the t stuff, there's no extra t's floating around, and we have one q and one dq in terms of the q stuff. First, it's going to be useful to factor out all the stuff that's a part of q, meaning negative 1 over RC. We want to just have q kind of by itself. Next, we want q on the other side with the dq, so we'll divide by q minus c times the EMF and multiply by dt on both sides to put the t variables on the other side. Now what we want to do is integrate both sides once we've separated the variables. We've been assuming we're starting with an uncharged capacitor, but if the capacitor is initially charged, then you could just change that lower bound to something else. Our upper bound is the charge q on the capacitor after some time t has passed. So on the left, when we take the indefinite integral, we end up with the natural log of q minus c times the EMF. And on the right, the definite integral of dt is just t, and bounded from 0 to t, we just end up with t minus 0, or just t. Expanding out the left-hand side, we end up with the natural log of q minus c times the EMF, all minus the natural log of just negative c times the EMF. Then we can make use of a well-known logarithm property. So instead of subtracting two logarithms, we can divide their inputs and then take the logarithm of that. We're almost there. Remember, we're trying to solve for q here. So now we take the exponential of both sides to remove the logarithm on the left, and then we multiply by negative c times the EMF. Now we just add c times the EMF on both sides and factor it out, and that completes the derivation. We figured out the charge q on the capacitor as a function of time using only a single application of the loop rule on the RC circuit. To figure out the current through the circuit, because I is equal to dq by dt, all we have to do is take the derivative of the charge with respect to time. We can pull the constant CE out and just take the derivative of what's left in parentheses. The derivative of 1 is just 0, and the negative e to the negative t over rc becomes positive 1 over rc times e to the negative t over rc. You just use the chain rule here. So whenever we take the derivative of e to some function, you just multiply e to that function by the derivative of that function. And just canceling out the capacitances completes the derivation for the current. This is the current as a function of time for a charging capacitor. That wasn't too bad, and actually, as we're about to see, the derivations for the discharging capacitor are even easier than that. We start with our loop rule in the discharging scenario, and remember that here, in order to keep the current positive, since the direction of the current is already correct, we have to awkwardly call I negative dq by dt, since the charge on the capacitor is decreasing. so dq by dt is negative. Then putting those two equations together, we ended up with this equation below. Because we want all the q's on one side and all the t's on the other side, we divide by q and multiply by dt. And now we're ready to integrate each side, so the charge we're assuming starts at some initial charge q naught and ends up at some charge q, and the time starts at t equals 0 and ends up at some time t. Then the definite integral on the left evaluates to the natural log of q minus the natural log of q naught, and the right just ends up being negative t minus 0 all over rc. We can make use of our favorite log property again, because we're trying to solve for q here. Then all we have to do is take the exponential on both sides and multiply by the initial charge of the capacitor on both sides, and we're left with the charge on the capacitor as a function of time. We remember if we want the current, what we're really after is the negative derivative of the capacitor's charge with respect to time, and we can pull out the initial charge, which is constant. Then all we gotta do is pull out a negative 1 over RC, and that just about does it. So in each scenario, all we needed was a single application of the loop rule, and we were able to figure out the charge on the capacitor and the currents through the circuit as a function of time, just by applying integral calculus to the differential equation.